I'm now going to introduce our next speaker. Our next speaker is online, perfect, Dr. Dan Vilenchik. And his talk is a quantitative approach for measuring the engagement of students in e-learning platforms. So Dan Vilenchik holds a PhD in computer science from Tel Aviv University. He did a postdoc at UC Berkeley and UCLA. He's currently a tenured member of the Electrical and Computer Engineering School at Ben-Gurion University. His research includes various aspects of machine learning, such as challenges of high-dimensional data, explainable AI, natural language processing, and multidisciplinary projects. Dan, if you just want to say hello to make sure we can hear you.
Hi, you hear me?
Perfect. Yes, we can. Thank you. All right, whenever you're ready, go ahead.
Okay, so thank you for the kind introduction. So this is a joint work with Professor Yaakov Gal. He's also from Ben-Gurion University, and a master's student, Chaviv Hershkovitz. And the paper where all the full details and the results can be found is cited below. Okay, so let's dive in. So we're going to talk about disengagement in e-learning system. I'm going to introduce the system, and everything will be self-contained. So disengagement is a burning issue in many disciplines and platforms and businesses. And in a very high level definition is a user that starts using the system. At the beginning, he's very enthusiastic, but then as time progresses, he just loses interest and stops engaging with the system. He can totally drop off or engage very rarely or in very low capacity. And unlike traditional industries where you had a contract and you would have to let the operator or the provider know that you are disengaging, that you are terminating the contract, current day disengagement in online platforms in general, you have no idea that the user disengaged, right? He doesn't let you know, and hence the problem. And in this study, we studied the problem of disengagement in a very popular math learning platform. It's called Matific. I'll show you in a second how it looks like. So this it operates in over 23 countries, many languages. It gears towards kids from kindergarten and to elementary school. So it covers a wide range of levels, and it has many platform settings. It can be handset, it can be a web interface, and it has a self-guided mode where a student plays by himself, or it could be in class. And this study is about the self-guided utilization, where a student at his leisure time plays with the system. It was also endorsed by Israeli Nobel Prize winner. In Hebrew, it's called 10 fingers, and I guess everywhere you learn to count on your 10 fingers, but that's the local name. So I'll show you how it looks like. An episode. So an episode consists of several games. So here you see the screen. Do you see the Matific? I'll see the screen. So it's very so there is cute animations, right? And then you answer, of course, you get nice feedback, and then you progress. Right? So you progress inside the episodes, like make a mistake. So you progress inside the episode, and everything is recorded. So the data is recorded, the time it took you to make the response, was it a correct response or not? At the end of the episode, did you rerun the episode, or even the game? Did you watch again? So everything that the student does is recorded at the back end of Matific. And we had really the pleasure of collaborating with, I'll go back to the slides, with Shimon Shoken and Raz Kupperman from the Hebrew University. They initiated this system, they built it, and they let us use this very unique data this study is about 20,000 home students, and try to address the problem of disengagement. So here are some, ballpark figures for the Matific data. 80%. So here we see log number of users. So it's on a logarithmic scale, and here we see the number of episodes open. So an episode is like the game you just saw. It contains several mini games inside the episode. So 80% of students opened less than 20 episodes, and that's it. So they played up to 20 episodes. So you see, most of them opened just one episode. So they opened one episode, decided that it's not for them, and just churned, disengaged. And also in terms of time, right? So here I'm showing in terms of throughput, but also in terms of time. Most students churn after a few minutes. So, clearly it's a problem for Matific. They put a lot of effort into this platform, and then they want people to engage, and they want to prevent disengagement, and they want to try to understand why people disengage and also predict it. So if I can predict disengagement, maybe I can intervene right before the user leaves. So here is an example of bad intervention. We all know these emails that we get from Coursera offering us special offers, and then we just were even more angry for them bothering us, and we never go back. But you can plan better interventions if you have both an idea why the user disengaged and also a good prediction when the user is going to disengage. And in this talk, I'm going to tell you about this study. So let's see. Yeah. Okay, so ideally what we want is to have an algorithm M. The input to the algorithm would be the history of the student's activity up to a certain time t, where we decide, so after 10 minutes of activity, we want to predict disengagement. Now this cutoff time t, we'll talk about it, of course. The more data you have, the more accurate your prediction will be, but then the more chances that the user have already disengaged and your prediction is useless. Plus maybe some metadata like the age, location, but this is problematic in terms of privacy. So many apps now, to be compliant with all kinds of GDPR privacy, they don't provide any metadata. So basically you can think about it just as a student's activity. And the output would be a prediction whether the user will play or churn meaning disengage, in a certain time interval. So maybe I'm measuring the student's activity in the first 10 minutes, and I want to know, based on that activity, will he play in the next 24 hours? Yes or no? So a few problems that we're going to address right now is how to define churn or disengagement in terms of time. It's not a straightforward definition. And also, what would we like the output of the algorithm to be? Do we want a binary output? Yes, no, disengage, yes or no. Maybe the probability of disengagement, or something more meaningful as the engagement level, right, on a Likert scale. So what makes the problem of predicting disengagement hard? So the first thing is the definition of disengagement, which is not a trivial task. And there are many papers about disengagement in e-learning platforms, citizen science, in all related areas. And when you go paper by paper, you see that the definitions change, and it's always a challenge. Do you want to define it by time, by performance, throughput, right? And of course, different definitions can lead to different conclusions and also to different performance of the algorithm. So let's say a student plays very little, but over a long period of time. So how do you label him? Engaged, disengaged, or maybe a student that always chooses easy tasks. a student that plays regularly but doesn't complete the task. So we saw that an episode completes of several tasks. So maybe he's frustrated and leaves at the end and returns, but never completes the task. So each aspect is very interesting, but then you have to commit to some definition. So let's see, let's say a concrete numeric example to illustrate it. So suppose my first cutoff is 10 minutes, dropping out within 10 minutes, dropping out within 24 hours, or before completing 10 questions. So let's say we have a student that started at 10 in the morning, and then stopped at 10:05, then came back at 10:20, and then stopped at 10:25. So according to definition A, he's labeled as engaged because he played after the 10 minutes cutoff. But according to B, he dropped before he disengaged because he never returned after 24 hours. And then we don't know even what about C, right? So you see the different definitions, and they're all used in the literature. Different definitions lead to different results. And of course, are they meaningful? We have to see in the context of the application. So for example, in Matific, if we know that 80% churn within the first 10 minutes, so 10 minutes would be a good cutoff. So here are some definitions or what people looked at from the literature, leading papers in the field of disengagement. So the left one was on a course, an online course like Coursera. So they were talking about participation, coming to the course, so being absent or coming to the course, and about consuming content. So participation and consuming content. Another paper talked about being passively engaged, again, only consuming content, not producing one. And the third one about a decrease in both consumption and participating, right? So you see, it's kind of vague. When you want to turn it into a computational framework, you have to commit to numbers, and then it can become more messy. Another thing that makes the problem hard is the statistics. So there are many different reasons for disengagement. Maybe the episodes or those questions are too long, too short, too hard, too easy. Maybe you're distracted with other apps that run on your computer or on your handset. And the statistics, as I told you in the beginning, the statistic that we have are what questions the user chose to solve and all kinds of timing. So in a second, I'll show you the exact features, but the features are all game features or features that relate only to the handset, to the application. We don't ask the student how interested he is. There are no questions or about his state of mind, if he's distracted or other things that's running. So also that's a challenge because the statistics are limited and a priori it's not clear how relevant they are to model and predict disengagement and to what accuracy. So in this work, we offer a new way to model disengagement. And we propose a computational toolkit for predicting disengagement, and we applied it in real world. We also, so we came back to Matific with the results and showed it to them. And at the end, they took some of our advice, incorporated it into the system. So the features that we collected, and some of them we had to engineer from the raw data. So the data is raw, it's just logs, login logs and all the event logs. So we had to engineer features from the event logs. So one set of features related to time aspects. So for example, the average response time of the student, also standard deviations. So a student that the standard deviation with respect to the response time. And we'll see that it plays a key role in our pipeline, the standard deviation. Another set of features concern the difficulty aspects. So the average difficulty. So for every question, we have a metadata, which is the average difficulty, the difficulty as Matific views it. So Matific labels the questions also according to which grade it belongs and the difficulty level of the question in the series. So we had this data, and we also computed we can compute the average difficulty according to the error rate, the false rate, the average false rate on that question from all the other students. So we have the empirical difficulty and also the proclaimed difficulty of Matific, and throughput aspects. For example, how many questions the user opened, how many questions he completed, how many new episodes he opened because he can rerun the same episode a few times, and the false rate, how many questions he got wrong. So in total, we had 17 features that we collected, and with them we trained a machine learning pipeline that I'm going to discuss now to predict churn. So any questions so far about definitions? Okay, so we'll start with the baselines before we get to our approach. So I'm not sure if this crowd is, how many of you are into the details of machine learning. It's not going to be technical. I just mentioned that we chose 3 algorithms that draw on different, let's say, optimization functions. So random forest, which is the go-to algorithm whenever you have a tabloid data, and we had a tabloid data, and therefore neural networks, deep neural networks, all that stuff is less relevant, because when you have data which is in form of a table, then random forest, variants of random forest give typically the best performance. And they draw on intuition from information theory. We also ran Gaussian naive Bayes, which is a probabilistic algorithm, and linear discriminant analysis, which has a geometric algebraic intuition. So different algorithms to run our data. We tried different cutoffs, 10 minutes and 24 hours. So again, the problem is defined. We collect data in the first 10 minutes, and on those 10 minutes, we have the label. So the label is, does he play after those 10 minutes or never comes back? After those 24 hours, never come back. So the cutoff defines both the period where we label churn, after 10 or after 24 hours, and also the observation period. So we look at the data in that period, and then we do the forecasting. And the evaluation metric that we chose was AUC, area under the curve. So that's the ROC curve, the precision, the true positive, and 1 minus the false negative rate, which is customary where you look at unbalanced data. So accuracy is less informative, and in our case, it's highly unbalanced because, as we've seen, the churn rate is around 80%, depending on the metrics, but it's far from being balanced. So these are the definitions, and let's see what we got in like the first try, where you just run those off-the-shelf algorithms in a standard train test cross-validation scenario, where you take part of the input for training, so that's with the label, and then you test on data that the algorithm never saw, and you check the accuracy. So this is the accuracy for different cutoffs. So 10 minutes, 1 hour, 3 hours, 24 hours. So as expected, when you have more data on the student, the performance increases. So from 10 minutes to 24 hours, it increased by 10 points, which is quite significant. And we see that the best algorithm was LDA, and the AUC was the best AUC that we got was 72, also random, 72. All of them were here at least pretty similar, around 70, which is okay. It's not very high, but again, it shows how difficult the problem is. Here, what we see is a projection, a histogram of the projection of the data on the first linear discriminant vector. So LDA basically gives you a vector on which you project the data. So the vector is computed according to some optimization problem, target that I'm not going to, of course, discuss, but it makes sense. So here we see the projection of the 17-dimensional data on this one dimension, on this one vector. And we see it for the two classes. So we see it for the class that churned and for the class that didn't churn. On the y-axis, you have the number of users, and on the x-axis, you have the projection. Now, it's unitless, so I mean, the units don't say anything, but what you can see is that the overlap is very large. And hence, this is why the accuracy is not that good, because users that churn or not churn in the first 10 or 1 hour or 24 hours, they behave quite similarly. Here you see the difference, right? So you see that here is the difference, and here you have another tail. So you see, so there are places where only users that don't churn or churn have a specific characteristic, but the overlap shows how difficult the difficulty of the problem. So far we defined the problem, which is, definition is quite intuitive, but at least the features that we collected and this standard pipeline of applying machine learning to your features turned out to be not that meaningful to capture disengagement. The AUC was low. Plus, in terms of explainability, if you want to know why the student disengaged, so you can maybe perform feature selection, but again, it's not clear how informative those features will be with this performance. So now we're going to describe our approach. Our approach was based on a principal component analysis on PCA. So I guess most of you have heard of PCA because it's a visualization tool that that's the bread and butter, where you want to have a nice figure in your paper and you have high dimensional data, in our case 17 dimensions, and you want to show it in 2 dimensions. Then you apply PCA. It's an unsupervised method, so that's one advantage. You don't need the label. So you're not dependent on the definition, on the cutoff. You just take the data, take the statistics. You don't care if it's churn or not churn. So that's one. So this is an important thing. And it applies the simple linear algebra manipulation called principal component analysis. It reduces the dimensionality of the data by projecting it to vectors, like in the LDA case. So it projects the 17-dimensional data to vectors. You choose how many vectors you want. And they are ordered in decreasing order of importance. And if you project it to one vector, so you have a one-dimensional problem, and so on. And those PCs, those vectors, those principal components, are linear combination of the original features. And that's going to be important because then you can look at the vectors if you're not too scared, and I guess this crowd is not scared of math, so you can actually zoom into the vector, look at we'll do it in a second together, look at the entries and see what meaningful patterns in the data emerge. So one thing that you have to do when you run PCA is to compute the explained variance. Since you are reducing dimensionality, so you want to know, okay, if I reduce it just to one dimension, how authentic this one dimension is, how much does it capture of the 17 dimensions? And so the first, in our case, that's called the script plot. And in our case, the first 3 dimensions captured almost 50% of the variance, which is a lot in such noisy data, very subjective, you know, large variance between students, many use cases, many ages. So 50% is a lot. And these are the principal components. So what do we see in this table? Here we have the feature name, the 17th feature. So for example, the first feature was the episode max difficulty. So that's the maximum difficulty that the student chose before he disengaged, or in that observation period, right? In the first 24 hours, what was the maximum difficulty? What was the average difficulty? What was the standard deviation of the average? And so on and so on. And so these are the features, and the PCs are vectors. So this is the leading principal component. That's a vector in 17 dimensions on which we project the data of the students. And we see that we have a few prominent entries. And the first 3 entries, they correspond to the max difficulty, average, and standard deviation. And then we have abandon rate and distinct episode rate. So if we look at PC1, so students that have a large projection on PC1, they have high max and average difficulty, but also a high standard deviation. So we call those students that have a large projection on PC1 explorers. So, I mean, this is, of course, a subjective decision of us to label them, but looking at those entries, it made sense. The second PC is more straightforward. We see the average difficulty and the false rate. So you see standard deviation is almost 0. And here is 0.33. Here it's also almost 0. So the main feature that made us term this direction exploration is the standard deviation. So here we have the difficulty, the false rate. So those are students that a large projection means that they have that they take on hard question, not so many, right? This is negative sign. So because the questions are hard, they solve less of them, also less and also less of episodes, and the minimum difficulty is also large. So we see that we can call this PC1 the difficulty direction. And then the last principal component, the largest entries are on pace, so that the response time, standard deviation over the response time, and another thing that relates to the response time. So the fact that the PCs split in this semantic way, it's also nice. I mean, it's not obvious. It could have been a complete mishmash of entries without any pattern, but when exploring them, we saw those 3 patterns emerge. Okay, so that's the first component. And then, so this is standard, right? People run PCA, but the innovation that we did, we looked at the dynamics, the user dynamics. So we have 10 minutes or 24 hours or whatever your time period is. And what we did is for every user, we constructed a time series, a one-dimensional time series, which is the projection of the data of the user depending on the cutoff, but if it's 24 hours, so it's every 10 minutes, we take the observational data in the first 10 minutes, first 20 minutes, every 10 minutes, we take the data and we project it on the PC and we get a trend line. We get some trend line. So for example, if this is PC2, the difficulty, so we see that this is a user that has an increasing projection on PC1. So we know that this user, he is solving harder and harder questions, unlike this student that started hard, but it was hard for him, and then it decreases, the difficulty decreases, and this user has a variable rate. So the difficulty increases, decreases, increases, decreases, right? So this is going monotone up, monotone down, and this is variable. So after we created those user dynamics, we labeled them with the trend of the time series. So it could be monotone up, monotone down, or variable, or fixed. So it could be fixed, like, a dead person's heart rate, it's fixed. And then, of course, it's users that churn very early, no change. And our hypothesis, which is also anchored in cognitive theories, in psychological theories, is that variability leads to engagement. And I think that the nice thing about this work is that, I mean, it's hard to, and we've seen it, we heard it in previous talk, that it's hard to quantify in a tight way abstract notions like variability of diversity of engagements, variability of engagement. How do you quantify it in a way that's succinct, computationally feasible, and then gives a good result? And I think that this is a nice example of how this framework where it can be done. And our hypothesis was that variability leads to engagement. So in this table, we'll see a verification of this hypothesis. So we have three possibilities. We have time series projected on PC1, which is exploration, PC2 difficulty, and PC3 is the pace, the time axis. So we see that 36% of all time series were fixed, and their time in the system was 0.10 hours, so like 6 minutes on average, and we have the net time activity in minutes. So out of those 6 minutes, the net activity time was 1.8. And then monotone up, we see that monotone up and down, we see more than fixed, and we see a big step, a big jump in variability. So the variable time series, the time in the system was much higher, and their net activity was much higher. So that's the exploration. If we go to the difficulty axis, so monotone up, those are students that choose harder and harder and harder questions, and at the end, they get frustrated by the difficulty and they drop from the system. And that's 15 hours on average. Monotone down, it's students that want to, take easier and easier questions. And maybe it's a bit more fun. Still, it gets boring after a while, drop the system. And then the variable is again the longest. And here we have the pace. So monotone up, students that play faster and faster. Monotone down, they play slower. Maybe it means that they also increase their difficulty or they pay more attention. And then again, the variable plays the highest. So that was nice to see that there is a correlation between our corroborating our hypothesis that variable users stayed longest in the system. And then when we went back to this prediction, we got the same AUC here. So we got 70, the AUC was 70. So we didn't improve on the AUC, but first, we didn't use any label. So it was completely unsupervised. We just look at what the users did. We didn't look into the future. So that's one important thing. You don't need training data, or at least no label. And we got the same accuracy. And the second thing, our pipeline was grounded in theory. So at least there was a good explanation why did we predict. So we predict that if you are, so we had a cutoff, all the monotone and fixed we predicted as churn, and the variable were predicted as not churn. And also we played with the number of times that it changes. So also for variable, you can count how many times it changes trend. And that also played a role. So if it changed trend only once, we still labeled it as churn. And if it changed more than once, then we only labeled it as not churn. And also it gives you, I think, a nice non-binary way of describing engagement. right? So it's not just engage, not engage. You can measure the level of engagement. For example, how many times you change trend. Okay, so to conclude, so I presented you the Matific platform, and we had really unique access to this real-world data, no simulation, no synthetic data, real-world home student data. And we presented a very intuitive approach using PCA, which is also explainable, and you can also visualize it. We defined the user dynamics approach and used it to predict engagement levels, and at the end, churn. Some limitations of the approach. So we had only a single data set, a single platform, a Matific, and we also looked only at home users. So we didn't look at what happens in the classroom. In the classroom, it's a different setting because the teacher assigns the student with tasks, and they have to perform it. And if not, the teacher he observes them and he motivates them. But still, it's interesting to measure engagement, but we didn't have access to this data. We could have checked more definitions of churn, not just time, and maybe run more algorithms. But all in all, I think it was a quite comprehensive study. That's it. Thank you.